What if I told you the universe is constantly whispering to us, not in words or light, but in ripples that stretch and squeeze the very fabric of space and time? These cosmic murmurs are gravitational waves, and they're rewriting everything we thought we knew about the cosmos. Picture this: two black holes, each with the mass of dozens of suns, locked in a deadly dance billions of years ago. Their collision sent shockwaves racing across the universe at the speed of light, warping space-time itself, and in 2015, for the first time in human history, we detected them. That moment didn't just prove Einstein right. It flung open a brand new window into the universe, one where we can literally hear the hidden symphonies of colliding stars, merging galaxies, and perhaps even the echoes of the Big Bang. Gravitational waves are more than just scientific curiosities. They're cosmic messengers, carrying secrets from the most violent and energetic events in existence. Before them, astronomy was like watching a silent movie. Now we've unmuted the universe. These ripples reveal the invisible. Black holes too dark to see, neutron stars spinning faster than kitchen blenders, and cosmic cataclysms that defy imagination. And here's the astonishing part: every new detection shatters old assumptions. We've found black holes heavier than theory predicted, witnessed mergers that shouldn't have been possible, and even caught hints of exotic objects we can't yet explain. Each discovery is like peeling back another layer of reality, showing us just how much we don't know. Today, we're diving into 30 of the most groundbreaking revelations brought to us by gravitational waves, discoveries that have reshaped physics, challenged our understanding of the cosmos, and even hinted at mysteries beyond Einstein's wildest dreams. From the first historic detection to the latest jaw-dropping findings, we'll explore how these space-time ripples are uncovering hidden dimensions of the universe, one pulse at a time. So buckle up. By the end of this journey, you'll never look at the night sky or the silent emptiness of space the same way again, because as you'll soon see, emptiness isn't empty at all. It's thrumming with the echoes of creation itself. The moment that changed astronomy forever arrived on September 14, 2015, at 5:51 in the morning. That's when twin detectors in Louisiana and Washington, part of the Laser Interferometer Gravitational Wave Observatory, LIGO for short, caught a whisper from the cosmos. A signal so faint it had traveled for 1.3 billion years, stretching and squeezing spacetime by less than 1,000th the width of a proton. Yet that almost imperceptible wobble told an incredible story. Two black holes, one 29 times the mass of our Sun, the other 36, had spiraled into each other at half the speed of light. In a fraction of a second, they merged into a single, more massive black hole, converting 3 times the mass of our Sun into pure energy, rippling outward as gravitational waves. What made this detection earth-shattering wasn't just the event itself, but what it proved. A century earlier, Albert Einstein had predicted these ripples in his theory of general relativity, but even he doubted we'd ever detect them. The distortions were too tiny, the universe too vast, yet here was the smoking gun, space-time itself ringing like a bell. The signal matched Einstein's equations down to the last decimal, confirming that gravity isn't just a force, it's the warping of the cosmos's fabric by massive objects. But LIGO discovery did more than validate a theory. It unveiled a hidden universe. Before 2015, black holes were cosmic phantoms, their existence inferred by their gravitational pull on surrounding matter. Now suddenly we could hear them collide. The data revealed details no telescope could catch: the black holes' masses, their dizzying spins, even the final, violent moments of their merger. It was like switching from grainy black and white footage to high-definition surround sound for the very first time. The implications rippled far beyond physics textbooks. This detection opened an entirely new branch of astronomy, one where we don't just see the universe but listen to its vibrations. It proved that gravitational waves could carry untouched stories across billions of years, free from the distortion or absorption that muddles light. And perhaps most thrilling, it hinted that this was just the first note in a much grander cosmic symphony. Because if two black holes could send such a clear signal, what else was out there waiting to be heard? Just 2 years after that first historic detection, gravitational waves delivered another bombshell, this time with a cosmic light show to match. On August 17, 2017, LIGO and its European counterpart, Virgo, caught a very different kind of ripple in spacetime. Unlike the silent mergers of black holes, this signal came with fireworks. For the first time ever, we witnessed the collision of two neutron stars, city-sized corpses of dead suns, each so dense that a teaspoon of their material would weigh 1 billion tons. The real magic happened when telescopes around the world swiveled toward the source. Within hours, observatories detected a blazing jet of gamma rays followed by a glow across every wavelength, from X-rays to radio waves. This wasn't just a gravitational wave event. It was the dawn of multi-messenger astronomy, where we could study the same cosmic cataclysm through both ripples in spacetime and light. The data painted an extraordinary picture. As the neutron stars spiraled together, they shredded each other apart, flinging ultra-hot debris into space that glowed with the brilliance of 1,000 supernovae. What made this collision so revolutionary was the treasure trove of science it unlocked. For decades, astronomers had debated where heavy elements like gold, platinum, and uranium were forged. The neutron-star merger answered that question spectacularly. Spectra from the afterglow revealed fingerprint-like signatures of these metals being synthesized in real time, proving that the universe's most precious elements are literally forged in the heart of these violent collisions. But the surprises didn't stop there. The event also settled a long-standing puzzle about gamma-ray bursts, those mysterious, ultra-powerful flashes in deep space. Now we knew at least some of them originate from neutron-star mergers. Even Einstein's theory got a new test. Scientists compared the arrival times of gravitational waves and light to confirm they travel at the same speed, another triumph for general relativity. Perhaps most breathtaking was the sheer coordination it revealed across the global scientific community. Over 70 observatories on every continent and in space joined forces to study this single event, marking a new era of collaborative astronomy. It was as if the universe had handed us a Rosetta Stone, a single cosmic event decoded through multiple languages of light and gravity. And just like that, we realized gravitational waves weren't just another way to observe the cosmos. They were the missing piece that tied everything together. If you thought black holes merging was a rare cosmic spectacle, prepare to have your mind blown. Gravitational waves have revealed something astonishing. These monstrous collisions happen way more often than anyone ever predicted. Before LIGO started listening, astronomers estimated we might catch one black hole merger every few years if we were lucky. But the universe had other plans. In just the first few months of observations, LIGO detected not one, but multiple black hole smash-ups. Suddenly, scientists realized these events weren't cosmic rarities. They were happening as often as once a week in the observable universe. That's like walking into a quiet room expecting to hear a single pin drop, only to find an entire percussion section going wild behind the curtain. What made this so surprising was how it overturned decades of theory. Most models suggested black hole pairs should be rare, since forming them requires very specific conditions like two massive stars born close together, surviving supernova explosions, and then avoiding being flung apart by galactic forces. But the sheer number of mergers detected suggests black holes are finding each other far more efficiently than we imagined. Some might get trapped in dense stellar environments like globular clusters, where gravitational tango partners are plentiful. Others could form directly from collapsing gas clouds in the early universe, bypassing the star stage entirely. the implications ripple across astronomy. If black holes merge this often, they're shaping galaxies in ways we never accounted for. Every collision flings the newly formed black hole at incredible speeds, like a cosmic slingshot, which could explain why some galaxies have wandering black holes far from their centers. Even more mind-bending, all these mergers mean supermassive black holes grow faster than we thought, feasting not just on gas and stars but on each other. Perhaps the weirdest twist is what this says about the early universe. Some of the merging black holes detected are so massive, they shouldn't exist if they formed from stars alone. That's led scientists to speculate about hierarchical mergers, where one black hole eats another, grows bigger, and then collides again like a snowball rolling downhill. If that's happening, the universe might be littered with black holes far heavier than our models predicted, silently reshaping cosmic history one merger at a time. Every new detection adds another piece to this puzzle, proving that when it comes to black holes, reality is stranger and far more violent than fiction. For decades, black holes came in two distinct cosmic sizes: stellar mass black holes, the collapsed remnants of massive stars weighing a few times our Sun, and supermassive behemoths lurking in galactic centers, millions or even billions of times heavier. But gravitational waves revealed something lurking in the cosmic shadows, black holes that didn't fit either category. These elusive in-between monsters, known as intermediate mass black holes, had been theorized for years, but catching them in the wild was like trying to spot a ghost. Then, in 2019, LIGO and Virgo detected a signal that changed everything. The ripple in space-time told a staggering tale. A black hole 66 times the mass of our Sun had just merged with another 85 solar masses. The result, a final black hole clocking in at 142 solar masses, the first definitive proof of an intermediate mass black hole. This wasn't just a missing link, it was a cosmic game-changer. Stellar black holes form from dying stars, but no star could ever collapse into something this heavy. The physics simply doesn't allow it. Supermassive black holes grow over eons, feasting on gas and stars, but how they get their initial seed mass was one of astronomy's biggest unsolved puzzles. Now suddenly we had evidence of black holes bridging that gap, suggesting a possible stepping stone in their evolution. The implications are profound. Some of these intermediate black holes might form in dense star clusters, where smaller black holes repeatedly collide and merge like contestants in a gravitational wrestling match. Others could be ancient relics from the early universe, born in chaotic environments where massive gas clouds collapsed directly into black holes without ever becoming stars. Either way, their existence helps explain how supermassive black holes grew so big so quickly by gobbling up these middleweight counterparts along the way. But here's where it gets even wilder. The 66 solar mass black hole involved in this merger was already an enigma. According to stellar physics, it shouldn't exist. When massive stars die, they often undergo a process called pair instability, where their cores become so hot that matter and antimatter particles annihilate each other in a runaway explosion, leaving no black hole behind. For stars between about 50 and 130 solar masses, this process should prevent black holes from forming entirely, yet there it was, defying expectations. This discovery didn't just fill a gap in our classification system, it ripped open new questions about how black holes form and evolve. Are there entire populations of these intermediate mass black holes hiding in plain sight? Could they be the dark architects shaping galaxies in ways we're only beginning to understand? With every new gravitational wave detection, we're peeling back layers of a cosmic mystery that's far stranger and far more chaotic than we ever imagined. Black holes aren't just cosmic vacuum cleaners sitting motionless in space, they're spinning, and some are rotating at speeds that defy physics as we know it. Gravitational waves have revealed these celestial powerhouses whirling so fast, they stretch the limits of Einstein's equations. Take the merger detected in 2020, where one black hole was spinning at nearly the maximum possible rate, a dizzying 95% of the speed of light. At that velocity, space itself gets dragged around the black hole like taffy, warping reality in ways we're only beginning to comprehend. What makes these extreme spins so baffling is how they upend traditional models of black hole formation. Conventional wisdom suggested most stellar mass black holes born from collapsing stars should spin moderately, since stars tend to rotate slowly by cosmic standards. But the data tells a different story. Some of these black holes are spinning so rapidly, it's as if they were launched from a cosmic slingshot. One theory suggests they might be the products of previous mergers, where two smaller black holes collided at just the right angle, transferring their combined angular momentum into a single, ultra-fast spinner. Another possibility, they could be feasting on gas and matter from a companion star in just the right way, revving up like a top spun by an invisible hand. The implications ripple through astrophysics. A black hole's spin isn't just a curiosity, it shapes the environment around it, influencing how matter falls in, and even how energy erupts from its poles in blistering jets. Extreme spins could also warp spacetime so severely that they create ergorgens, zones where nothing can stand still, not even light. And if these hyper-spinning black holes are more common than we thought, they might be powering some of the universe's most energetic phenomena, from quasars to gamma-ray bursts, in ways our models never accounted for. Perhaps the most mind-bending revelation is what these spins say about the nature of black holes themselves. Einstein's equations predict a speed limit, a point where spinning faster would cause the black hole to tear apart the fabric of spacetime. Yet some detections come alarmingly close to that edge, hinting at physics operating in regimes we've never tested. Are there black holes out there pushing past these limits? Could they be revealing cracks in our understanding of gravity itself? With every new gravitational wave detection, we're not just hearing the universe's whispers, we're decoding the secrets of its most violent, twisted corners. Some of the black holes detected through gravitational waves don't just challenge our understanding of space, they might rewrite the history of the universe itself. Hidden in the data are tantalizing hints that certain mergers involve objects so ancient they predate stars, galaxies, even light. These could be primordial black holes, hypothetical relics forged in the chaotic furnace of the Big Bang's first moments. Unlike their stellar descendants, which form from collapsing stars, primordial black holes would have sprung into existence from extreme density fluctuations in the infant cosmos, where patches of space were so crammed with matter they pinched off into singularities. The idea isn't new. Physicists like Stephen Hawking toyed with it decades ago, but gravitational waves are now offering the first concrete evidence. Take the infamous mass gap black hole detected in 2019, the one weighing 66 solar masses. Stellar evolution can't explain it, but primordial origins could. In the universe's first second, regions denser than the surrounding spacetime might have collapsed directly, creating black holes across a vast spectrum of sizes, from microscopic to thousands of times the sun's mass. These ancient survivors could have lurked undetected for billions of years, occasionally colliding and sending ripples we're only now picking up. If confirmed, the implications would be staggering. Primordial black holes could solve multiple cosmic mysteries in one swoop. For one, they're leading candidates for dark matter, that invisible glue holding galaxies together. While most dark matter searches focus on exotic particles, primordial black holes, especially those between asteroid and moon masses, could account for at least part of the missing mass. Their widespread presence might also explain how supermassive black holes grew so large so quickly in the early universe, seeding galaxies far sooner than current models allow. But the wildest possibility, some primordial black holes might still be hanging around, drifting through space like cosmic ghosts. A handful of theories even suggest one could be hiding in our own solar system, its gravity subtly tugging on distant objects beyond Neptune. While that speculative gravitational wave astronomy is finally giving us the tools to test these ideas. Every unusual merger, like those with unexpectedly high masses or odd spins, adds another piece to the puzzle, nudging us closer to answering one of cosmology's biggest questions. Did black holes exist before the stars, quietly shaping the universe from the very beginning? The more we listen to these space-time ripples, the more the cosmos whispers back with surprises. Einstein's theory of general relativity made a bold claim: gravitational waves should race through the cosmos at the speed of light, undisturbed and unyielding. But for a century, this prediction sat untested, like a cosmic dare waiting to be answered. Then came the neutron star collision of August 17, 2017, an event that turned the universe into the ultimate physics lab. When LIGO and Virgo detected the ripples from those colliding neutron stars, telescopes across the globe captured the accompanying flash of light: gamma rays, X-rays, even visible light pouring from the wreckage. Here was the perfect experiment: two messengers, gravity and light, traveling side by side across 130 million light-years of space. The question was simple: would they arrive together? The answer was a resounding yes. After painstaking analysis, scientists found the gravitational waves and light reached Earth within 2 seconds of each other. A trifling gap considering the journey's length and the fact that light might have been slightly delayed by interstellar gas. This near-perfect alignment wasn't just a victory for Einstein. It reshaped our understanding of reality itself. Gravity and light, though seemingly unrelated, are deeply intertwined, both bound by the universe's ultimate speed limit. But why does this matter beyond confirming a century-old theory? Because it rules out entire classes of alternative physics models. Some theories of quantum gravity or modified gravity suggested gravitational waves might travel slower or faster than light, especially if they leaked into hidden dimensions or interacted with dark matter. The detection slammed the door on those ideas, proving spacetime's fabric behaves exactly as relativity predicts, even under the most extreme conditions. The implications ripple through cosmology. If gravitational waves and light always travel in lockstep, it means we can use them as synchronized cosmic clocks, triangulating events with unprecedented precision. It also hints at something deeper: that gravity, often seen as the odd force out, shares a fundamental kinship with electromagnetism and the other forces. Perhaps most thrillingly, it gives us a new tool to probe the universe's expansion. By comparing gravitational wave distances with light-based measurements, we might finally crack the mystery of dark energy, the force accelerating the cosmos's expansion. This discovery wasn't just about checking a box in Einstein's ledger. It revealed a universe where the most violent events broadcast their secrets in perfect harmony, where spacetime's vibrations and light's shimmering waves dance to the same rhythm. And in that harmony, we're finding clues to the cosmos's grandest designs. Einstein's general relativity has survived every test thrown at it for over a century, but gravitational waves are pushing it to limits even he couldn't have imagined. Near black holes, where gravity twists spacetime into knots and matter reaches densities beyond comprehension, his equations face their ultimate trial. And here's the twist: every ripple we detect is proving Einstein right in ways that border on the uncanny. Take the infamous ring-down phase after two black holes collide, a phenomenon as precise as it is violent. As the newly merged black hole settles, it vibrates like a struck bell, emitting gravitational waves at specific tones dictated by relativity. LIGO detections match these predictions with staggering accuracy, down to the very frequencies Einstein's math foretold. It's as if the universe itself is whispering, "See, I told you so," but the real surprises come from the edges of plausibility. Some mergers produce black holes spinning so fast they nearly tear spacetime apart, yet relativity holds firm. Others involve objects with masses that defy stellar physics, warping gravity in ways that should break the rules but don't. Even the bizarre phenomenon of precession, where orbiting black holes wobble like spinning tops mid-collision, plays out exactly as Einstein predicted. These aren't just confirmations, they're stress tests in cosmic laboratories where gravity is 1 billion times stronger than anything in our solar system. Yet gravitational waves aren't just rubber stamping old theories, they're revealing where relativity might bend. One tantalizing anomaly popped up in 2020 when a merger produced signals slightly mismatched with expectations. Was it noise or a hint of new physics? Some theorists speculate that near the event horizon, quantum effects or hidden dimensions might tweak relativity's rules. Others wonder if black holes are messier than we thought, trailing clouds of exotic matter that distort their gravitational signatures. What's revolutionary is how gravitational waves let us probe these questions directly. Traditional telescopes see only light's afterglow, but ripples in spacetime carry unfiltered snapshots of gravity's raw power. A single merger can reveal whether black holes drag spacetime around them like molasses as relativity insists, or if some unseen force alters the fabric of reality in extreme conditions. Each detection tightens the screws on alternative theories, from modified gravity to string theory. And the stakes, nothing less than understanding how gravity behaves where it's strongest, and whether Einstein's masterpiece, like Newton's before it, might one day need an update. Because if relativity ever does crack, gravitational waves will be the first to sound the alarm. Until then, every collision, every ripple is a love letter from the universe, written in the language of warped spacetime, signed by Einstein himself. What if some of the ripples in spacetime we've detected aren't from black holes at all, but from something even stranger? A handful of gravitational wave signals have left scientists scratching their heads, their patterns just slightly off from what black hole mergers should produce. One tantalizing possibility: these anomalies could be the first whispers of wormholes, cosmic shortcuts predicted by Einstein's equations but never observed. Imagine a tunnel through spacetime itself, where matter and gravity waves might pass between points separated by billions of light years. If real, these structures wouldn't just warp space, they'd rewrite the rules of cosmic travel. The theory hinges on subtle quirks in gravitational wave data. When black holes merge, their signals follow a predictable crescendo, a rapid chirp as they spiral inward, followed by a fading ring down as the new black hole settles. But a few detections show peculiar echoes afterward, like spacetime itself is reverberating. Some researchers suggest these echoes could be waves bouncing off the mouth of a wormhole, its exotic geometry acting like an acoustic chamber for gravity. Others point to oddities in the signal shapes, where the frequencies dip or rise in ways that don't quite match black hole physics. It's as if the universe left breadcrumbs hinting at doorways we've yet to open. But wormholes aren't the only exotic explanation. Another candidate, gravastars, hypothetical objects that mimic black holes but are actually bubbles of vacuum energy wrapped in ultra-thin shells of matter. When these objects collide, they might produce gravitational waves with distinctive fingerprints, subtle differences in how the waves dampen or interact. Then there's the wild card of cosmic strings, infinitely thin, unimaginably dense flaws in spacetime left over from the Big Bang. If these strings snap or vibrate, they could send out bursts of gravitational waves unlike anything from black holes. The challenge is separating cosmic mirages from genuine breakthroughs. Noise in detectors, unforeseen astrophysical processes, or even quirks in data analysis can mimic exotic signals. But the payoff for confirming any of these phenomena would be astronomical. Wormholes, if stable, could revolutionize our understanding of spacetime structure. Gravastars might reveal new states of matter at densities beyond neutron stars, and cosmic strings, they'd be a direct window into the universe's first moments, a fossil from when reality was hotter and denser than the core of a supernova. For now, these ideas lie at the edge of known physics, too compelling to ignore but too speculative to confirm. Yet every anomalous gravitational wave brings us closer to answering one of science's biggest questions. Does the universe harbor shortcuts, hidden layers, or cracks in space-time itself? One thing's certain, if even a fraction of these signals turn out to be real, the cosmos just got a whole lot weirder. Among the strangest relics possibly lurking in the cosmos are cosmic strings, threads of pure energy thinner than a proton but stretching across the universe, left over from the fiery chaos of the Big Bang. These hypothetical fractures in space-time, if they exist, would be unlike anything else we've detected. Not objects, not waves, but flaws woven into the very fabric of reality itself. Imagine the universe as a cooling sheet of ice with cracks forming as it hardens. Cosmic strings would be those cracks, except instead of splitting water molecules, they're defects in space-time structure, carrying unimaginable density and tension. A single inch of cosmic string could outweigh Mount Everest. Gravitational waves might be our only hope of finding them. Unlike black holes or neutron stars, cosmic strings wouldn't glow or collide in ways telescopes could spot. But if one snapped or kinked, perhaps due to intersecting with another string or quantum fluctuations, it would send a shockwave through space-time, a burst of gravitational waves with an unmistakable fingerprint. These wouldn't be the familiar chirps of merging black holes, but sharp, erratic spikes like static on a cosmic radio. So why haven't we found them yet? Part of the challenge is their sheer subtlety. While a snapping string could release as much energy as a supernova, most of that would pour into distorting space-time itself, leaving only faint ripples for detectors like LIGO to catch. Worse, their signals wouldn't follow the clean, predictable patterns of orbiting objects. Instead, they'd be messy, one-off bursts, easily drowned out by background noise or mistaken for glitches in the detectors. Yet the hunt continues because the payoff would rewrite physics. Cosmic strings are predicted by many theories unifying quantum mechanics and gravity, including string theory. Finding one would offer direct evidence that the universe underwent dramatic phase transitions in its first moments, like water freezing into ice, locking these defects into the cosmos's structure. They might even explain some of the universe's largest-scale features, like the bizarre cold spots in the cosmic microwave background or the odd clustering of galaxies across billions of light-years. The search is pushing detectors to new extremes. Scientists are scouring existing gravitational wave data for statistical anomalies that might hint at strings. Future observatories like the space-based LISA could be sensitive enough to catch the low-frequency tremors from strings stretching across galactic distances. And if we do detect one, it wouldn't just confirm a wild, theoretical prediction, it would give us a time machine back to the universe's first trillionth of a second, when reality was so hot and dense that space-time itself could crack. For now, cosmic strings remain ghosts in the data, elusive, alluring, and just plausible enough to keep us listening. But in a universe full of gravitational whispers, the faintest signals often carry the loudest revolutions. Right now, in the hearts of galaxies millions of light-years apart, supermassive black holes are locked in a dance so slow it makes tectonic plates seem speedy. These cosmic heavyweights, millions or even billions of times the mass of our Sun, often come in pairs, orbiting each other for eons before finally merging in what would be the most violent event since the Big Bang. But here's the catch: we've never actually seen two supermassive black holes in this orbital embrace. The reason? Their gravitational waves hum at frequencies too low for current detectors to hear. That's about to change, and when it does, it'll rewrite the story of how galaxies grow. Imagine trying to detect the vibration of a tuning fork that takes years to complete a single cycle. That's the challenge with supermassive black hole binaries. Unlike their stellar mass cousins, which zip around each other in seconds before colliding, these giants move at a glacial pace, emitting gravitational waves with wavelengths spanning light years. LIGO and Virgo are deaf to these ultra-low frequencies. It's like expecting a violin to play the bass line of a symphony. But upcoming observatories like LISA, the Laser Interferometer Space Antenna, are being built specifically to listen. Slated for launch in the 2030s, LISA will consist of 3 spacecraft flying in a triangular formation millions of miles apart, laser beams connecting them like the world's most precise cosmic ruler. Free from Earth seismic noise, it'll catch those deep, rumbling waves with frequencies measured in microhertz oscillations so slow, a single wave cycle could last hours. Why does this matter? Because supermassive black hole binaries are the universe's ultimate architects. Nearly every large galaxy harbors one of these monsters at its core, and when galaxies collide, as they often do, their central black holes eventually pair up. Tracking these duets would reveal how galaxies stitch themselves together over cosmic time. Are the mergers messy, with black holes getting kicked off course by gravitational kicks? Do they stall for billions of years before finally coalescing, or do they merge cleanly, sending shockwaves through their host galaxies? The answers are hidden in those low-frequency waves waiting to be decoded. But the real jackpot would be catching a merger in action. When 2 supermassive black holes finally spiral inward, their collision would unleash gravitational waves with more energy than all the stars in the observable universe combined, a literal spacetime tsunami. The signal could last weeks or even months in LISA data, carrying details about the black hole's masses, spins, and even the shape of spacetime near their event horizons. It might also solve a long-standing mystery: why some galaxies, like our Milky Way, have oddly quiet central black holes while others blaze as quasars. The key could lie in how these mergers funnel or disrupt surrounding gas. And then there's the dark horse of this cosmic drama: intermediate black hole binaries. Theory suggests medium-weight black holes, thousands of solar masses, might also pair up in dwarf galaxies or globular clusters. LISA could spot these too, bridging the gap between stellar mass mergers and their supermassive counterparts. It's a whole new layer of the universe's soundtrack, one that's been playing in the background since the first galaxies formed. When we finally tune in, we won't just be hearing black holes collide, we'll be listening to the very rhythm of cosmic evolution. Every revolution in physics starts with a crack in our understanding, a tiny inconsistency that grows until the old framework shatters. Right now, gravitational waves might be revealing the faintest tremors along the seams between Einstein's gravity and the bizarre world of quantum mechanics. These 2 pillars of physics have stood side by side for a century, yet they speak entirely different languages. General relativity paints gravity as the smooth curvature of space-time, while quantum mechanics insists everything, even space itself, is pixelated into tiny, jittering fragments. Reconciling them is the holy grail of modern physics, and gravitational waves could be the Rosetta Stone we've been waiting for. The clues lie in the most extreme environments in the universe: black hole mergers where gravity reaches unimaginable strengths and spacetime gets stretched to its limits. Near the event horizon, quantum effects should theoretically warp spacetime in subtle ways, imprinting faint signatures on gravitational waves. Imagine listening to a symphony where one violin is slightly out of tune. That's what physicists are searching for: anomalies in the ringing of merged black holes that don't quite match Einstein's predictions. Some theories suggest quantum gravity might cause spacetime to froth at microscopic scales, creating a faint noise in the signal. Others propose that black holes could leave quantum echoes, repetitions in the gravitational waves caused by extra dimensions or loops in spacetime's fabric. The hunt is already underway. Teams are sifting through LIGO data for statistical glitches, patterns that might hint at quantum gravity's fingerprints. One tantalizing possibility involves Hawking radiation, the theoretical glow emitted by black holes as they slowly evaporate. While too faint to detect directly, some models suggest this quantum process could subtly alter the gravitational waves emitted during a merger, like a whisper layered beneath a shout. Even more speculative ideas involve quantum hair, the notion that black holes might carry hidden quantum information on their surfaces, tweaking their gravitational wave emissions in ways we could decode. But the real breakthrough might come from a different cosmic laboratory: neutron stars. These ultra-dense corpses of dead stars are nature's perfect quantum gravity experiments. Their cores crush matter into states so extreme that even quarks, the building blocks of protons and neutrons, might dissolve into a soup of more fundamental particles. If spacetime has a quantum structure, the gravitational waves from colliding neutron stars could carry its signature, perhaps as distortions in how the waves propagate or unexpected harmonics in their frequencies. What makes this search so electrifying is the sheer breadth of possibilities. String theory, loop quantum gravity, holographic principle. Each framework makes different predictions about how quantum gravity should sound in gravitational waves. A single detected anomaly could vault one theory to prominence while relegating others to history. And if we're extraordinarily lucky, we might stumble upon something none of them predicted, a cosmic wild card that forces us to rethink reality from the ground up. We're still years, maybe decades, away from definitive answers. Current detectors aren't sensitive enough to spot most quantum gravity effects, and the math involved is fiendishly complex. But next-generation observatories like the Einstein telescope or Cosmic Explorer could change everything. With sensitivities 10 times greater than LIGO, they might catch the whispers of quantum spacetime we're straining to hear today. This isn't just about testing theories, it's about discovering whether the universe plays by rules we can even comprehend. Because if gravitational waves really can reveal quantum gravity, we won't just be solving a physics puzzle. We'll be decoding the universe's deepest layer of reality, written in ripples that have traveled across space and time to tell us how existence truly works. Dark matter has been the universe's most frustrating puzzle for decades, an invisible substance making up 85% of all matter, yet refusing to interact with light or anything else we can directly detect. We know it's there because of its gravitational pull, bending galaxies and sculpting the cosmos, but its true nature remains one of physics' greatest unsolved mysteries. Now, gravitational waves might offer a backdoor into the dark universe, not by seeing dark matter, but by listening to how it warps the ripples in spacetime. One radical possibility: dark matter isn't just passive cosmic scaffolding. It could be clumpy, forming dense clouds or even exotic objects that gravitational waves must travel through. Picture a ripple on a pond passing through patches of thicker water. Its speed or shape might subtly change. If dark matter interacts with itself or distorts spacetime in ways we don't expect, mergers between black holes or neutron stars could carry faint imprints of their journey through these hidden landscapes. Already, scientists are scouring LIGO data for anomalies like signals arriving slightly delayed or warped that might betray dark matter's presence along the wave's path. Then there's the wild card: primordial black holes. These hypothetical relics from the Big Bang could solve two puzzles at once. If they exist in certain mass ranges, they might be dark matter, lurking unseen throughout galaxies. Gravitational waves could confirm their existence by catching mergers between these ancient objects, ones too small or distant for telescopes to spot. The key would be in the statistics. If detectors start finding more black hole mergers in specific mass ranges, say between 1 and 1,000 solar masses, it could signal a hidden population of dark matter black holes weaving through the cosmos. But the most mind-bending idea involves dark matter altering gravitational waves themselves. Some theories suggest dark matter particles could have tiny charges or interact with gravity in ways that subtly shift a wave's frequency or polarization. It's a long shot, but if future observatories like the Einstein telescope detect signals that twist or flicker unpredictably, dark matter might be the culprit, tweaking spacetime's vibrations like a cosmic DJ. The beauty of this approach is its sheer creativity. Instead of waiting for dark matter to reveal itself in a lab or telescope, gravitational waves let us hunt for its shadow. The way it bends, delays, or distorts the universe's most energetic events. Every merger becomes a flashlight shone into the dark, and if we're lucky, we might finally catch a glimpse of what's been hiding in plain sight all along. Neutron stars are nature's most extreme laboratories, cosmic pressure cookers where matter gets crushed into states so bizarre, they defy the laws of physics as we know them. These ultra-dense remnants of dead stars pack more mass than our Sun into a sphere the size of Manhattan, creating gravitational fields so intense, a marshmallow hitting the surface would strike with the force of a nuclear bomb. But here's the catch, we've never been able to peek inside one. The sheer density bends light so severely that even our most powerful telescopes can only study their surfaces. That's where gravitational waves change everything, because when two neutron stars collide, the ripples they send through spacetime carry encoded secrets about what's happening deep in their cores. The breakthrough came with that fateful detection in August 2017. As the neutron stars spiraled toward each other, their gravitational waves revealed not just their masses and orbits, but something far more profound, the way their shapes deformed under each other's crushing gravity. Like two rubber balls pressed together, they stretched and flattened in ways that depended entirely on how their interiors resisted the strain. This tidal deformation is the key to unlocking neutron star matter. The stiffer their interiors, the more they'd resist distortion, leaving a distinct fingerprint in the gravitational wave signal. What LIGO and Virgo found was astonishing. The data suggested these neutron stars were so dense, their cores might be a quantum soup of free-floating quarks, the fundamental particles that normally bind together inside protons and neutrons. But the possibilities get even wilder. Some theories suggest that under such extreme pressure, neutrons themselves might dissolve into a bizarre state called hyperonic matter, where exotic particles like hyperons, cousins of protons and neutrons with strange quarks, bubble up from the quantum foam. Others speculate the cores might host boson condensates, a frictionless superfluid where matter behaves like a single, giant quantum wave. Gravitational waves give us a way to test these ideas by comparing the observed tidal deformations with predictions from different models. If the stars deform less than expected, it points to a stiffer interior, perhaps with free quarks. If they squash more easily, it might mean hyperons or other exotic particles are softening the core. The collision's aftermath added another clue. As the neutron stars merged, telescopes caught the resulting fireball glowing with telltale signatures of heavy elements like gold and platinum. The brightness and duration of that glow depended on how much matter was flung out, which in turn hinged on how the star's core behaved at the moment of impact. A squishier interior would eject more material, while a stiffer one would slurp most of it into the newly formed black hole. The data leaned toward the latter, suggesting these neutron stars were just barely dense enough to avoid immediate collapse, teetering on the edge of becoming black holes themselves. What's unfolding is a revolution in nuclear physics. Laboratories on Earth can never recreate these conditions. Our most powerful particle smashers only reach a fraction of neutron star densities. But by studying gravitational waves from these mergers, we're effectively turning the universe into a particle accelerator, probing states of matter that haven't existed naturally since the first seconds after the Big Bang. Every new neutron star collision adds another piece to the puzzle, inching us closer to answering one of science's biggest questions: what happens to matter when gravity wins? And the implications stretch beyond curiosity. Understanding neutron star interiors could reveal why some of these objects spin at mind-bending speeds, powering the universe's most magnetic objects, magnetars. It might explain mysterious fast radio bursts, those split-second cosmic signals that could be neutron stars cracking under internal stress. Some theories even suggest that deep inside these stars, quarks might form Cooper pairs, creating a superconductor that generates the most powerful magnetic fields in existence. The next time LIGO or Virgo catches a neutron-star merger, listen closely. Those ripples aren't just cosmic noise, they're the universe whispering the recipe for matter itself, cooked under pressures we can scarcely imagine. And with each new collision, we're not just learning about distant stars, we're decoding the very fabric of reality. For centuries, astronomers wondered where the universe's heaviest elements, gold, platinum, uranium, came from. These cosmic treasures couldn't be forged in ordinary stars or even supernova. Their creation required something far more extreme. Then, in August 2017, gravitational waves handed us the answer on a silver, or rather golden platter. When LIGO and Virgo detected the collision of two neutron stars, telescopes around the world captured something unprecedented, a kilonova, an explosion so powerful it briefly outshone entire galaxies. And in that blinding flash, science finally witnessed the universe's ultimate alchemy, the moment atoms heavier than iron were born in furious cascades of nuclear fusion. This wasn't just another explosion. Kilonovae are cosmic crucibles where conditions are so extreme they force neutrons into atomic nuclei at breakneck speeds, creating unstable elements that rapidly decay into gold and other precious metals. The process, called rapid neutron capture, or the R process, had been theorized for decades, but until gravitational waves pointed the way, we'd never caught it in action. The smoking gun came from the afterglow spectrum, which bore the unmistakable fingerprints of heavy elements forming in real time. Calculations suggest this single event produced an astonishing 50 Earth masses of gold alone, along with uranium and other rare metals. Suddenly, the jewelry on your finger and the circuitry in your phone had an origin story written in neutron stars' violent deaths. But kilonovae aren't just about bling, they're reshaping our understanding of cosmic chemistry. Before this discovery, most models assumed supernova were the primary source of heavy elements. Yet the sheer quantity of gold and platinum generated in this single kilonova hinted that neutron star collisions might dominate the universe's supply. Some estimates now suggest these mergers could account for half of all elements heavier than iron in the cosmos. That means the atoms in our bodies, our technology, even our planet's core might trace back to ancient stellar smash-ups billions of years ago. The real magic lies in how gravitational waves cracked this mystery. Without them, the kilonova would have been just another flash in the sky, lost in a sea of cosmic explosions. But the ripples in spacetime pinpointed exactly where and when to look, turning a random burst into a targeted scientific jackpot. It's like having a treasure map where X marks not just the spot, but the precise moment gold would bubble up from the cosmic forge. And with each new neutron star collision detected, we're gathering more clues about how these events seed galaxies with the building blocks of planets and life itself. What's truly mind-blowing is the timescale. The R process unfolds in seconds as the merger's outgoing shockwave rips neutrons from the shattered star's crusts, bombarding nearby atoms in a frenzy of nuclear reactions. That's faster than some stars take to rotate once. Yet in that blink of cosmic time, enough gold is forged to fill oceans, scattered across space to someday coalesce into new worlds. Talk about a productive afternoon, and the discoveries keep coming. Recent observations suggest kilonovae might not all look alike. Some glow blue from lighter elements early on, then redden as heavier metals form and block certain wavelengths of light. Others might produce far more debris if the neutron stars are lighter or spin faster, creating brighter, longer-lasting fireworks. Gravitational waves help decode these variations by revealing the star's masses and spins before they collided, giving context to the light show that follows. The implications stretch far beyond astrophysics. If neutron-star mergers are indeed the universe's primary goldsmiths, their frequency dictates how quickly galaxies become enriched with heavy elements and thus how soon rocky planets like Earth could form. It might even hint at why some stars host planetary systems richer in precious metals than others. Every kilonova detected is a snapshot of the universe's chemical evolution, a clue to how we went from a cosmos filled with hydrogen and helium to one brimming with the diversity of the periodic table. So the next time you see gold glinting in sunlight, remember, its journey began in a cataclysm so violent it warped spacetime itself, and thanks to gravitational waves, we now have a front-row seat to the cosmic foundry where matter gets remade. Einstein's equations painted black holes as the ultimate cosmic minimalist objects so simple, they could be described with just three numbers: mass, spin, and electric charge. This radical simplicity, dubbed the no-hair theorem, suggests that no matter how complex an object is before collapsing into a black hole, all its intricate details, its hair, get shorn off at the event horizon, leaving behind a perfect bald sphere of warped spacetime. But what if that's not the whole story? Gravitational waves are now probing whether black holes might secretly cling to remnants of their past, hiding faint imprints of their formation history like cosmic fingerprints. The no-hair theorem isn't just a quirky idea, it's a cornerstone of general relativity, tested every time LIGO detects a black hole merger. According to Einstein, the final moments of a collision should produce gravitational waves with a clean, predictable pattern. A rapid chirp as the black holes spiral inward, followed by a fading ring down as the newly merged black hole settles into its simplest possible state. Any deviations from this smooth decay could hint at hidden structures, perhaps quantum fields clinging to the black hole's surface, or even exotic matter from its progenitor star that somehow survived the collapse. Here's where gravitational waves become cosmic detectives. By analyzing the ring-down phase with exquisite precision, scientists can search for subtle overtones, extra frequencies in the signal that shouldn't exist if black holes are truly bald. Think of it like striking a bell. A perfect, smooth bell rings with a pure tone, but a bell with cracks or imperfections produces dissonant harmonics. In 2021, a team combing through LIGO data reported tentative evidence of these overtones in a black hole merger, sparking fierce debate. Were they seeing the first hints of hair or just noise masquerading as physics? The implications are staggering. If black holes do retain traces of their past, it could solve one of physics' biggest paradoxes, the black hole information problem. Quantum mechanics insists that information about a particle's state can never be destroyed, yet the no-hair theorem suggests black holes obliterate it completely. Any gravitational wave signature of hair might bridge this gap, revealing how information smuggles itself out, perhaps encoded in those very ripples in spacetime. But the plot thickens. Some theories, like string theory, predict black holes could have soft hair, low-energy quantum excitations on their event horizons too faint to detect with current instruments. Others suggest magnetic fields or dark matter might leave permanent marks on a black hole's gravitational wave profile. Even more radical is the possibility that what we call black holes aren't singularities at all, but exotic objects like gravastars or fuzzballs, whose complex interiors would definitely sport gravitational hair. The hunt is accelerating. Next-generation detectors like the Einstein telescope will measure ring-downs with 10 times the precision of LIGO, potentially spotting overtones too subtle to catch today. And if they do, it wouldn't just rewrite our understanding of black holes, it could unveil entirely new laws of physics lurking just beyond the event horizon, waiting to be decoded in the universe's quietest whispers. Beneath the loud crashes of black hole mergers and neutron-star collisions, the universe murmurs a quieter secret, a faint, ceaseless hum woven from countless cosmic events too distant or ancient to distinguish individually. This is the gravitational wave background, the static of space-time itself, created by the overlapping ripples of every collision, explosion, and vibration since time began. Imagine standing in a bustling city. You might hear a siren blaring nearby or a conversation across the street, but beneath it all is the muffled roar of traffic, footsteps, and distant voices blending into a single ambient noise. That's the universe's gravitational soundtrack, a chorus of whispers from merging black holes, spinning neutron stars, and even the echoes of the Big Bang, all layered into a cosmic drone. Detecting this background is like trying to hear a single raindrop in a thunderstorm. Current observatories like LIGO and Virgo are fine-tuned for sharp, transient events, the cosmic equivalents of drum solos. But the stochastic background is more like the rustle of a million leaves in the wind, requiring a different approach altogether. Scientists are turning to pulsars, the universe's natural metronomes. These ultra-precise neutron stars spin with such regularity that their radio pulses arrive on Earth like clockwork unless space-time itself stretches or compresses in between, subtly altering their rhythm. By monitoring networks of these pulsars across the galaxy, researchers can catch the infinitesimal distortions caused by passing gravitational waves, effectively using the Milky Way as a galaxy-sized detector. The potential revelations are staggering. A strong background signal might reveal populations of black holes we've never seen, primordial ones from the universe's infancy, or swarms of intermediate mass black holes lurking in galactic cores. Some theories even suggest the background could carry traces of cosmic strings snapping in the void, or phase transitions from when the universe was a trillionth of a second old. Then there's the wild card, if inflation, the rapid expansion of the universe right after the Big Bang, was violent enough. It might have generated gravitational waves strong enough to linger as a detectable hum today. Finding that would be like uncovering a fossil from the very first moment of time, but the real magic lies in what this background could tell us about the universe's structure. Just as the cosmic microwave background gives us a snapshot of the cosmos 380,000 years after the Big Bang, the gravitational wave background could offer a glimpse into the dark ages, the mysterious epoch before stars ignited, when the universe was pitch black and filled only with roiling matter and radiation. It's a window into a time no telescope can see. The hunt is already yielding tantalizing hints. In 2023, several pulsar timing arrays reported a possible signal, a low-frequency rumble consistent with the combined gravitational waves from millions of supermassive black hole binaries. While not yet definitive, it's a whisper of what's to come. Future projects like the Square Kilometer Array radio telescope will monitor thousands of pulsars with unprecedented precision, potentially turning that whisper into a shout. What's at stake isn't just another line in astronomy's ledger. If we can decode this background, we'll be hearing the universe's hidden history, the sum of every cataclysm, every collision, every vibration that's ever rippled through space-time. It's the soundtrack of existence itself, playing on loop since the dawn of time, and we're finally learning how to listen. Right now, Earth-based detectors like LIGO and Virgo are listening to the universe's gravitational wave symphony, but they're only catching the high notes. The real cosmic bassline, the rumbles of supermassive black holes and the primordial echoes of the Big Bang, hum at frequencies too low for any ground observatory to hear. That's about to change with LISA, the Laser Interferometer Space Antenna, a revolutionary mission that will turn the solar system into the most sensitive gravitational wave detector ever built. Scheduled to launch in the 2030s, LISA consists of 3 spacecraft flying in a perfect triangular formation, trailing Earth in its orbit around the Sun. Connected by laser beams spanning 2.5 million kilometers, 6 times the distance to the Moon, they'll sense passing gravitational waves by measuring minuscule shifts in those beams, down to a fraction of an atom's width. Free from Earth seismic noise and atmospheric interference, LISA sensitivity will let it eavesdrop on gravitational waves with wavelengths so long, a single oscillation could take hours or even days to complete. What makes this so groundbreaking is the range of cosmic phenomena it'll unveil. While LIGO catches the violent mergers of stellar mass black holes, LISA will trace the stately dances of their supermassive cousins, monsters millions of times heavier, orbiting each other for millennia before colliding. These binary black holes, hidden in galactic cores, are the architects of cosmic structure, shaping galaxies through their gravitational pull. LISA could track thousands of them, mapping their masses, spins, and orbits with precision, revealing how they grow by feasting on gas, stars, and even each other. But the discoveries won't stop there. LISA might catch the moment a small black hole gets captured by a supermassive one, a process called an extreme mass ratio inspiral, where the smaller object spirals in over years, its orbit gradually decaying until it's swallowed. The gravitational waves from this death spiral would encode detailed information about the supermassive black hole's spacetime geometry, putting Einstein's theories to the test in regimes no lab could ever replicate. Then there's the hunt for the universe's first black holes. If primordial black holes formed in the chaos of the Big Bang, LISA could detect their mergers from cosmic dawn, events so ancient the stars and galaxies hadn't even begun to form. These signals would be time capsules from the universe's infancy, carrying clues about the conditions that birthed the very first structures in existence. Perhaps most tantalizing is LISA's potential to uncover entirely new physics. Some theories predict that cosmic strings, those hypothetical spacetime defects left over from the early universe, would vibrate at frequencies perfect for LISA to spot. Others suggest that if extra dimensions exist, they might subtly alter how gravitational waves propagate over interstellar distances, leaving fingerprints in LISA data. And if dark matter interacts with gravity in unexpected ways, those interactions might warp the signals from distant mergers. But LISA isn't just about hearing new cosmic players, it's about listening to the universe in stereo. By combining its low-frequency data with observations from LIGO, Virgo, and electromagnetic telescopes, we'll create a multi-band gravitational wave observatory covering the full spectrum from milliseconds to years. It's like upgrading from a tin can telephone to a surround sound system where every layer of the cosmos's soundtrack becomes audible. The mission also pioneers mind-bending technology. Each spacecraft must float in near-perfect free fall, shielded from solar wind and other disturbances by advanced thrusters. The lasers connecting them need to maintain stability across millions of kilometers, a feat requiring optics so precise they can detect a passing gravitational wave's gentle nudge, equivalent to measuring the distance from Earth to Alpha Centauri to within the width of a human hair. As LISA prepares to take its place in orbit, one thing is certain: the universe's quietest murmurs are about to become deafeningly clear. And when they do, we won't just be hearing black holes collide, we'll be tuning into the background hum of spacetime itself, a soundtrack 13.8 billion years in the making. Einstein's general relativity has ruled physics for over a century, its predictions matching observations with uncanny precision. Yet whispers of dissent linger. What if gravity doesn't quite work the way we think? Modified gravity theories propose to explain cosmic mysteries like dark matter and dark energy, suggest spacetime might bend under rules Einstein never imagined. Gravitational waves are now putting these radical ideas to the test, probing whether our understanding of gravity needs a rewrite, or if Einstein's vision holds firm against all challenges. One of the boldest alternatives is modified Newtonian dynamics, or MND. This framework suggests that on galactic scales, gravity strengthens slightly compared to Newton's and Einstein's predictions, eliminating the need for dark matter to explain how galaxies rotate. But MND faces a stiff challenge from gravitational waves. When black holes merge, their emitted ripples depend entirely on how spacetime warps under extreme gravity, and so far, every LIGO detection matches Einstein's equations to the last decimal, leaving no room for tweaks. The nail in the coffin, the neutron-star merger of 2017. The gravitational waves arrived within seconds of the gamma rays, proving gravity and light travel at identical speeds, something Mund struggles to explain without adding extra assumptions. Then there's scalar tensor theory, a class of models where gravity isn't just geometry, but involves an extra field permeating space. Some versions predict gravitational waves should arrive slightly distorted, carrying faint echoes or polarization patterns that deviate from general relativity. LIGO and Virgo have been hunting for these anomalies, particularly in the ring-down phase of black hole mergers, where exotic fields might leave subtle imprints. So far, no conclusive evidence has emerged, but future detectors like the Einstein telescope could spot discrepancies too small for current instruments. Perhaps the most tantalizing tests involve how gravitational waves propagate across cosmic distances. In Einstein's universe, these ripples should fade predictably as they stretch spacetime. But some modified gravity theories suggest waves might interact with dark energy or hidden dimensions, causing them to weaken differently over vast reaches. The gravitational wave background, the faint hum of countless distant mergers, could carry these fingerprints, revealing whether spacetime's fabric has hidden textures beyond relativity's smooth geometry. Yet with every test, Einstein's theory emerges unscathed. The fact that gravitational waves from colliding black holes match his century-old math so precisely is itself a marvel. It suggests that if modified gravity exists, its effects must be vanishingly subtle, or confined to domains we haven't probed yet, like the universe's first instance or the cores of quantum black holes. The stakes couldn't be higher. If even a single gravitational wave signal definitively breaks from general relativity's predictions, it would ignite a scientific revolution, forcing us to rethink everything from black holes to the Big Bang. But if relativity keeps passing every test, we're left with a deeper mystery. Why does dark matter seem to warp galaxies without bending spacetime in ways we can detect? The answer might lie not in rewriting gravity's rules, but in uncovering the invisible cosmic players we've yet to find. Either way, gravitational waves are the ultimate referee in this century-spanning debate, and every new detection brings us closer to knowing whether Einstein's gravity stands alone, or if the universe has been keeping deeper secrets all along. When two black holes collide, the resulting cosmic explosion doesn't just fade into silence. It leaves behind a newly forged black hole humming like a struck bell, its vibrations echoing across spacetime in a phenomenon called ring-down. These gravitational wave echoes aren't just cosmic noise, they're a precise fingerprint encoding everything from the black hole's mass and spin to the very shape of spacetime around it. Imagine tossing a pebble into a pond and watching the ripples. The way they spread and fade tells you about the water's depth and the pebble's weight. Ring-down works the same way, except instead of water, it's the fabric of reality itself vibrating. The magic lies in the mathematics. Einstein's equations predict that a newly merged black hole won't settle immediately. It will oscillate, shedding distortions in a series of gravitational waves at specific frequencies called quasi-normal modes. The loudest tones correspond to the black hole's fundamental properties, like a musical instrument's lowest notes, while fainter overtones reveal finer details, much like harmonics on a violin string. By decoding these frequencies, scientists can measure the black hole's mass and spin with staggering precision, sometimes to within a fraction of a percent. It's as if the universe handed us a tuning fork calibrated to the darkest objects in existence. But ring-down does more than just weigh black holes, it tests the limits of Einstein's gravity. According to general relativity, a black hole's ring-down should follow an exact pattern, a smooth, exponential decay as the waves lose energy. Any deviations, echoes, extra frequencies, or unexpected damping could hint at physics beyond Einstein. Some theories suggest quantum effects near the event horizon might leave faint imprints, like scratches on a record subtly altering the music. Others propose exotic alternatives to black holes, like wormholes or gravistars, which would ring down in entirely different ways. So far, every detection aligns perfectly with relativity, but future observatories like the Einstein telescope could spot anomalies too subtle for current instruments. One of the most striking discoveries came from a merger detected in 2019, where the ring-down revealed a black hole spinning at nearly the speed of light. The frequencies of its gravitational waves indicated a spin so rapid it was flirting with the cosmic speed limit, the point where Einstein's equations predict space-time would tear apart. Yet there it was, humming along just as relativity demanded, proving black holes can dance on the edge of physics without slipping over. What makes ring-down so revolutionary is its purity. Unlike the chaotic inspiraling phase of a merger, where black holes twist and distort each other's shapes, the ring-down is clean and predictable, a direct probe of the final black hole's isolated spacetime. It's the closest we've come to seeing a black hole's true form, not through light, but through the vibrations it leaves in the universe's fabric. And with every new merger detected, we're not just listening to the echoes of cosmic collisions, we're reading the hidden language of gravity written in the ripples of spacetime. Gravity isn't just a force, it's the great cosmic choreographer, orchestrating black hole mergers with mathematical precision. But sometimes the universe throws in a wild card, sending astronomers scrambling to rewrite their playbooks. Take the bizarre case of the black holes that refused to dance in sync. In 2020, gravitational waves revealed a merger so peculiar, it looked like the cosmic equivalent of a ballet dancer partnered with a breakdancer, two black holes spinning wildly out of alignment, their axes tilted at extreme angles. This wasn't just a minor quirk, it was a full-blown rebellion against everything theorists expected. Standard models predicted most merging black holes would spin in roughly the same direction, like graceful ice skaters holding hands in unison. After all, pairs born from the same stellar nursery should inherit similar rotations. Yet here were two cosmic heavyweights spinning almost perpendicular to each other, their chaotic waltz defying textbook explanations. The leading theory, these black holes didn't grow up together at all. They were strangers flung into each other's orbits by chance encounters in densely packed star clusters. Imagine a mosh pit at a concert where dancers keep swapping partners mid-song. In galactic terms, that's what globular clusters are like, ancient stellar metropolises where black holes could get gravitationally slingshotted into unexpected pairings, creating mergers with spins pointing every which way. Then there's the cosmic odd couple, a merger detected in 2019 featuring one black hole nearly 4 times heavier than its partner. Such extreme mass ratios are like pairing a sumo wrestler with a gymnast. The smaller black hole gets yanked around violently, tracing chaotic orbits before being swallowed whole. These lopsided mergers leave a distinctive fingerprint in the gravitational waves, a stuttering chirp that crescendos unpredictably as the lighter black hole stumbles through spacetime's twists and turns near its colossal partner. What's truly baffling is how these mismatched pairs form in the first place. Normally, binary black holes arise from twin massive stars that collapse in tandem. But a 4-to-1 mass ratio suggests one star must have evolved differently, perhaps losing huge amounts of material to a companion or exploding in an unusually weak supernova. Some astronomers speculate these oddballs might originate in active galactic nuclei, where swirling gas disks can trap black holes of vastly different sizes and force them together over time. The anomalies don't stop there. A handful of detections show black holes spinning backward relative to their orbit, like a figure skater spinning clockwise while circling counterclockwise. These retrograde spins could be smoking guns for chaotic formation histories, where black holes get captured into orbits that flip their rotational axes upside down. General relativity predicts such mergers should emit gravitational waves slightly differently, with distorted waveforms that could teach us how spacetime reacts when spun in reverse. Each of these cosmic outliers is more than just a curiosity. They're stress testing our understanding of how black holes live, die, and find each other in the dark. If black holes can merge in configurations this wild, it hints at a universe far messier and more dynamic than our tidy models predicted. Star clusters might be black hole matchmaking hubs, galactic centers could host violent blind date collisions, and ancient cosmic environments might have forged black holes with spins we've yet to even imagine. The deeper we listen, the clearer it becomes. Black holes don't follow rules, they write them, and every strange chirp in the data is another verse in their untamed cosmic saga. Just as a magnifying glass bends light to reveal hidden details, the universe has its own way of warping gravitational waves, an effect called gravitational lensing. When these spacetime ripples pass near massive objects like galaxy clusters or black holes, their paths curve, distorting the signals in ways that open new windows into the cosmos. The first hints of this phenomenon emerged in 2021, when researchers analyzing a black hole merger noticed something odd. The signal seemed to echo itself, as if the same event was being heard twice. The explanation: the gravitational waves had taken multiple paths around an intervening galaxy, some bending slightly more than others, creating a cosmic mirage that reached Earth at slightly different times. Gravitational lensing isn't new. Astronomers have used it for decades to study dark matter and magnify distant galaxies, but applying it to gravitational waves is revolutionary. Unlike light, which can be absorbed or scattered by cosmic dust, gravitational waves travel cleanly across the universe, making their lensed signals pristine probes of the massive structures they encounter. By measuring how these waves distort, whether they're stretched, split, or amplified, we can map the distribution of matter along their path, including the invisible dark matter that makes up most of the universe's mass. It's like turning space-time itself into a giant magnifying glass where the distortions reveal hidden cosmic blueprints, the most tantalizing possibility. Detecting microlensing, where smaller objects like lone black holes or dense dark matter clumps briefly warp passing gravitational waves. These subtle distortions could unveil entire populations of rogue black holes drifting between stars, or even exotic dark matter particles clumping in ways current telescopes can't see. In 2023, a team proposed that future observatories might catch these effects as fleeting glitches in wave signals, a slight dimming or frequency shift betraying an invisible lens's presence. But the real prize would be lensed waves from the cosmic dawn. If gravitational waves from the first black hole mergers were lensed by ancient galaxy clusters, their distorted signals could carry snapshots of the early universe's structure frozen in time. Unlike light, which took hundreds of millions of years to pierce the fog of the early cosmos, gravitational waves from that epoch would arrive unfiltered, their lensed paths encoding conditions no telescope could ever glimpse. What's emerging is a radical new tool for cosmology. By combining lensed gravitational waves with traditional light-based observations, we're building a multidimensional map of the universe, one where spacetime's twists and turns reveal not just what's out there, but how it's woven into the fabric of existence itself. Every lensed wave is more than a signal, it's a cosmic X-ray exposing the hidden bones of reality. Most of what we know about the Big Bang comes from ancient light, the cosmic microwave background, a snapshot of the universe when it was just 380,000 years old. But gravitational waves could take us back even further, to the universe's very first instance, when reality was so hot and dense that even light couldn't move freely. These primordial ripples, if we can detect them, would be the ultimate time capsule carrying unfiltered whispers from the birth of spacetime itself, the challenge. The gravitational waves from the Big Bang would be incredibly faint, stretched by the universe's expansion into ultra-low frequency hums far below what current detectors like LIGO can hear. But future observatories like the space-based LISA or ambitious ground-based projects such as the Einstein telescope are being designed to tune into these cosmic bass notes. Their goal: catch the echoes of inflation, the theorized period when the universe expanded exponentially in a fraction of a second. According to leading models, this violent stretching of space-time would have generated gravitational waves powerful enough to persist for billions of years, imprinting a unique pattern on the fabric of the cosmos. If we could detect this signal, it would revolutionize our understanding of the universe's origins. The cosmic microwave background gives us a baby picture of the cosmos, but inflationary gravitational waves would be like hearing the first cry, a direct probe of conditions when the universe was just a trillionth of a trillionth of a trillionth of a second old. These waves could reveal whether inflation really happened, how hot the Big Bang was, and even whether our universe is just one bubble in a vast multiverse. But the potential discoveries don't stop there. Some theories suggest the earliest moments of the universe might have produced other exotic gravitational wave sources, like cosmic strings, infinitely thin defects in spacetime that could have vibrated like guitar strings, sending out sharp bursts of gravitational waves. Others speculate that phase transitions in the newborn universe, akin to water freezing into ice, might have created gravitational wave backgrounds with distinctive frequency patterns. Even more radical is the idea that the Big Bang wasn't the beginning at all, but a bounce from a previous collapsing universe. Such a scenario would leave its own gravitational wave fingerprint. Detecting these primordial ripples won't be easy. The signals would be buried under noise from countless astrophysical sources, requiring exquisitely sensitive instruments and clever data analysis to tease out the faintest hints. But if we succeed, we'll have done something once thought impossible: peered beyond the veil of the cosmic microwave background into the universe's fiery first breath. And what we find there might not just rewrite the story of our cosmos, it could reveal entirely new chapters in the book of physics. Among the most extreme cosmic dances, gravitational waves might reveal a hypercompact star system's black holes locked in furious orbits with neutron stars, whirling so close they complete full revolutions in mere minutes. These bizarre pairings would push Einstein's theory to its limits, generating gravitational waves with a frenetic, high-pitched chirp unlike anything we've detected so far. Picture a neutron star 1 trillion times denser than a white dwarf skimming just above a black hole's event horizon, moving at a significant fraction of light speed. The tidal forces alone would stretch spacetime into knots, while the gravitational radiation emitted would be so intense it could theoretically be detected across millions of light years. What makes these systems so extraordinary is their sheer violence. Unlike the graceful spirals of merging black holes, a neutron star orbiting a black hole at such close range would experience relentless torture, its crust cracking under tidal forces, its magnetic field twisting into chaotic knots, and its very atoms getting shredded into streams of plasma. Some models suggest the neutron star might even be partially peeled apart, with each orbit shedding layers of material that spiral into the black hole in blazing arcs of X-rays. The gravitational waves from this process wouldn't just carry the clean tones of orbital motion. They'd be laced with dissonant harmonics from the star's deformation, like a bell ringing with cracks in its surface. The hunt for these systems isn't just about cosmic spectacle, it's a goldmine for fundamental physics. A neutron star's stubborn resistance to being fully torn apart would encode precise details about the nature of ultra-dense matter. By analyzing the gravitational wave frequencies, we could measure the star's tidal deformability, how much it squishes under the black hole's pull, which in turn reveals the properties of matter at densities unreachable in any lab. Some theories predict that under such strain, the neutron star's core might transition into exotic states like quark-gluon plasma or hyperonic matter, each leaving a distinct imprint in the waves. Then there's the space-time warping spectacle of the black hole itself. If the black hole is spinning rapidly, a likely scenario given its voracious consumption of matter and angular momentum, its ergorgon, the zone where space gets dragged around it like a whirlpool, could intersect the neutron star's orbit. This would create additional gravitational wave frequencies, a complex interplay of orbital and frame dragging effects that would test general relativity in regimes we've never probed. The resulting signal might even reveal whether black holes truly have no hair or if their event horizons hide subtle structures, the wildest possibility. Some hypercompact systems might not end in mergers at all. If the neutron star is dense enough and the black hole's spin is just right, the star could enter a quasi-stable orbit, dancing on the edge of annihilation for thousands of cycles before finally being swallowed. This prolonged death spiral would emit gravitational waves in a slowly shifting frequency, like a siren descending in pitch, giving us an unprecedented opportunity to study both objects in microscopic detail. Detecting these systems will require next-generation observatories. Current detectors like LIGO are tuned for the lower frequencies of black hole mergers, but hypercompact binaries would scream into the millihertz range, perfect for space-based detectors like LISA. By the 2030s, we might finally catch these cosmic duets, each one a laboratory for the most extreme physics the universe has to offer. And when we do, it won't just be a new class of objects we're discovering, it'll be a front-row seat to the universe's most brutal ballet, where matter and gravity collide in ways that defy imagination. Decoding the violent ballet of colliding black holes isn't just about listening to spacetime's ripples, it's about recreating those cosmic crashes in supercomputers so powerful they can warp virtual reality itself. This is numerical relativity, the mind-bending fusion of Einstein's equations and raw computational might that's transformed gravitational wave astronomy from guesswork into precision science. Before these simulations, physicists were like chefs trying to reconstruct a recipe by tasting the final dish. Now they're watching the entire cosmic kitchen in action, frame by frame. The challenge was monumental. Einstein's field equations are famously nonlinear, meaning small changes can snowball into chaotic outcomes, like a pencil balanced on its tip suddenly toppling in unpredictable directions. Solving them for merging black holes, where spacetime folds into knots and matter reaches infinite densities, required rewriting the rules of computation. Early attempts in the 1990s crashed supercomputers after mere milliseconds of simulated time. The breakthrough came when theorists like Franz Pretorius split spacetime into dynamic grids, allowing supercomputers to focus processing power where gravity's grip was most extreme, near the black hole's event horizons, while simplifying comma regions. It's like using a zoom lens on a camera, adjusting focus to capture both the swirling details and the broader scene. By the time LIGO detected its first gravitational waves in 2015, these simulations had evolved into staggeringly accurate predictors. The chirp-like signal from that historic black hole merger matched supercomputer models down to the waveform's subtle wiggles, confirming not just the detector's findings but relativity itself. But the real magic happened afterward when numerical relativity became the Rosetta Stone for translating gravitational waves into black hole biographies. By comparing LIGO signals against vast libraries of pre-calculated mergers, scientists could now extract details like the black hole's spins, masses, and orbital angles with shocking precision. It's akin to identifying a singer's height, age, and vocal training just by analyzing a 3-second audio clip. The simulations revealed phenomena no telescope could ever catch. Take the anti-kick effect, where merged black holes recoil at speeds topping 5 million miles per hour, launched by asymmetrical bursts of gravitational waves. Or the way rapidly spinning black holes drag spacetime around them like cosmic whirlpools, imprinting spiral patterns on their emitted waves. Some models even show merged black holes ringing like gongs, their surfaces vibrating at multiple frequencies that subtly distort the gravitational wave signal. Without numerical relativity, these nuances would be lost in the noise. But the revolution isn't just about interpreting data, it's about preparing for discoveries we haven't made yet. Supercomputers are now simulating wildly exotic scenarios, black holes plowing through neutron stars like cannonballs through foam, triple black hole systems dancing themselves into mergers, even collisions in warped spacetimes with extra dimensions. Each simulation is a dress rehearsal for potential detections, ensuring that when LIGO or future observatories catch something unprecedented, we'll have the tools to understand it. Perhaps most remarkably, these virtual experiments are becoming laboratories for fundamental physics. By tweaking Einstein's equations in simulations, say, adding hypothetical fields or altering gravity's strength, researchers can generate what-if waveforms to compare against real data. It's a way to hunt for physics beyond relativity without waiting for nature to provide the perfect test case. Already, some teams are simulating wormhole mergers or collisions in alternative gravity theories, creating templates that could one day prove our universe isn't quite as Einstein envisioned. The scale of these computations is staggering. A single high-resolution black hole merger can require months on thousands of processor cores, generating petabytes of data, enough to fill a library's worth of hard drives. Yet this computational alchemy is rewriting textbooks weekly. When LIGO detected a merger with a mysteriously lopsided mass ratio in 2019, numerical relativity clarified it wasn't a glitch but a rare cosmic pairing, a heavyweight black hole swallowing a lightweight companion hole. Another simulation revealed how certain neutron star collisions could briefly form a hypermassive neutron star before it collapsed into a black hole, solving puzzles about short gamma-ray bursts. What began as a theoretical exercise has become astronomy's crystal ball, a way to peer into gravity's darkest corners before we ever observe them. And as supercomputers grow more powerful, they're not just predicting gravitational waves, they're inventing new ways to listen. For centuries, astronomy meant one thing: light. Whether through the lens of Galileo's telescope or the digital sensors of modern observatories, we've pieced together the cosmos by studying photons across every wavelength. But gravitational waves didn't just add a new instrument to the orchestra, they rewrote the entire symphony. Suddenly, we're not just seeing the universe, we're feeling its vibrations, tasting its particles, and weaving these disparate signals into a richer tapestry than ever before. This is the era of multi-messenger astronomy, where gravitational waves, light, and even ghostly neutrinos converge to tell stories no single signal could reveal alone. The neutron star collision of August 2017 wasn't just a milestone, it was a manifesto. For the first time, gravitational waves alerted telescopes worldwide to swivel toward the same patch of sky, capturing the event in gamma rays, X-rays, visible light, and radio waves. But the collaboration didn't stop there. IceCube, the neutrino observatory buried in Antarctic ice, joined the hunt, searching for elusive particles that might have escaped the wreckage. Together, these messengers painted a portrait no single observatory could achieve. Gravitational waves traced the star's death spiral, gamma rays revealed the jet of energy screaming outward, and the kilonova's glow exposed the heavy elements forged in the crucible of collision. It was like witnessing a storm through sound, sight, and touch simultaneously, each sense filling gaps the others couldn't. What makes this approach revolutionary isn't just the volume of data, it's the synergy. Take gamma-ray bursts, those enigmatic flashes that puzzled astronomers for decades. When gravitational waves confirmed at least some originate from neutron star mergers, it wasn't merely an answer, it was a new way to calibrate the universe. By comparing the arrival times of gamma rays and gravitational waves, scientists verified they travel at the same speed, tightening the screws on Einstein's relativity. Meanwhile, the kilonova's light curve, how its brightness evolved over days, provided an independent measure of the universe's expansion rate, cross-checking results from other methods. It's as if each messenger is a witness in a cosmic courtroom, corroborating testimony to build an airtight case. Neutrinos add another layer of intrigue. These nearly massless particles, born in the hearts of collapsing stars and cataclysmic explosions, rarely interact with matter, allowing them to escape environments even light can't penetrate. If a supernova's gravitational waves give us the bass notes of collapse and its light paints the fiery aftermath, neutrinos are the inside scoop, a real-time feed from the core's most violent moments. Future detections might catch neutrinos from merging neutron stars, potentially revealing whether these collisions produce bizarre quark matter or even temporary black holes. The true power of multi-messenger astronomy lies in its ability to surprise. In 2020, astronomers linked a high-energy neutrino to a flaring blazar 4 billion light-years away, a discovery that suggested these distant, supermassive black holes might accelerate particles to energies beyond our most powerful colliders. Without the neutrino, the blazar's flare would have been just another flicker in the data. Without the light, the neutrino would have been an orphan, its origin forever unknown. Together, they opened a new window into particle acceleration in the universe's most extreme environments. This convergence isn't just changing what we know, it's reshaping how we explore. Observatories once operated in silos, their data analyzed by specialists in narrow wavelengths. Now, gravitational wave alerts trigger automated scans by telescopes worldwide, while neutrino detectors flag potential cosmic events in real time. The result is a global, interdisciplinary hive mind, where a signal in one channel sparks a coordinated rush to decode it across others. It's astronomy as a team sport, and the payoff is a universe that's suddenly speaking in surround sound. The next frontier, adding all cosmic messengers to the mix. Imagine a supernova's gravitational waves arriving hours before its light, giving telescopes precious time to prep for the explosion's first photons. Or a black hole merger's ripples revealing where to hunt for flashes from disrupted stars in its accretion disk. Some theorists even speculate that certain dark matter particles could produce correlated signals, gravitational waves from annihilation paired with gamma rays or neutrinos. Every new combination is another dial on the cosmic control panel, fine-tuning our understanding of reality. We're no longer just observers of the universe's grand spectacle. We're participants in a dialogue, learning to listen not just with our eyes, but with every tool physics allows. And as detectors grow more sensitive and coordination more seamless, one thing is certain: the most profound discoveries will come not from any single messenger, but from the moments their whispers align, telling stories deeper and stranger than we've dared to dream. One of the most beautiful aspects of gravitational wave astronomy isn't just the science, it's who gets to participate. While billion-dollar detectors like LIGO and Virgo capture the universe's ripples, the task of deciphering these signals isn't reserved for elite researchers alone. Thanks to projects like Einstein at home, anyone with a computer and an internet connection can join the hunt for cosmic collisions, turning everyday volunteers into citizen scientists shaping the frontiers of astrophysics. Einstein at home harnesses the collective power of idle computing cycles from thousands of volunteers worldwide. Here's how it works. When your device isn't in use, it crunches small chunks of gravitational wave data, searching for subtle patterns that might indicate faint signals buried in the noise. The project's distributed network has scanned through petabytes of information, equivalent to analyzing every book in the Library of Congress multiple times, and the results are staggering. Volunteers have helped identify multiple neutron stars, including exotic Black Widow pulsars that vaporize their stellar companions, and even contributed to gravitational wave detections by refining searches for continuous wave sources. This isn't just busy work. The algorithms powering Einstein at home are designed to catch signals too weak or too complex for traditional methods. Some gravitational waves, like the steady hum from lone spinning neutron stars, resemble a whisper in a hurricane requiring months of computational sifting to uncover. By dividing the task across countless devices, the project achieves sensitivity that even supercomputers struggle to match. One volunteer, a German electrical engineer named Bernd Maschenschork, famously discovered a previously unknown pulsar using his home computer, proving that groundbreaking science doesn't always happen in a lab. But the impact goes beyond raw data processing. Einstein at home has cultivated a global community of enthusiasts, from students to retirees, who gather in online forums to discuss their findings and troubleshoot analyses. For many, it's not just about contributing spare computing power. It's about being part of a collective journey to decode the universe. The project's transparent approach lets participants follow their contributions in real time, seeing how their machine's calculations fit into the broader puzzle. The democratization of discovery doesn't stop there. Other initiatives like Gravity Spy enlist volunteers to classify glitches in gravitational wave data, training AI systems to distinguish between real cosmic signals and instrumental artifacts. These cosmic noise detectives have categorized thousands of anomalies, improving detector sensitivity and even uncovering rare environmental interference patterns like disturbances from distant earthquakes. What makes these efforts revolutionary is their scalability. As gravitational wave astronomy expands with future detectors like the Einstein telescope set to generate exponentially more data, crowdsourced science will become indispensable. The next era of discovery won't just belong to scientists in white coats. It'll be shaped by classrooms, hobbyists, and curious minds worldwide, all contributing to a deeper understanding of spacetime's symphony. And in that collaboration, we're reminded that the universe doesn't just speak to experts, it whispers to anyone willing to listen. Among the cosmic cacophony of black hole collisions and neutron star mergers, there's one glaring absence. Where are the supernova? These titanic stellar explosions, long theorized to be gravitational wave powerhouses, have left detectors strangely silent. It's like tuning into a symphony and realizing the brass section never played a note. The absence isn't just puzzling, it's reshaping our understanding of how massive stars meet their explosive ends. Take the iconic Crab Nebula, the remnant of a supernova observed on Earth in 1054. When its progenitor star collapsed, it unleashed enough visible energy to outshine the moon for weeks. Yet if LIGO had been around back then, it likely wouldn't have heard a whisper. The reason lies in the physics of asymmetry. Gravitational waves aren't produced by perfectly spherical explosions. They require lopsided, chaotic motion, like a star's core sloshing violently or spinning so fast it flattens into a wobbly pancake before detonating. Most supernova, it turns out, might be far more symmetrical than we imagined, their cores collapsing inward like a neatly deflating balloon rather than a shattering champagne glass. But there's another twist: failed supernova. Some massive stars might collapse directly into black holes without the classic explosion, swallowing their own shockwaves before they can ripple outward. Imagine lighting a firework that gets sucked into a black hole mid-bang. That's essentially what could be happening in these dark, quiet collapses. These stealthy events could leave behind black holes with no supernova fireworks to announce their birth, their gravitational wave signatures too faint or fleeting for current detectors to catch. The silence has led scientists to rethink supernova diversity. Perhaps only a rare subset like hyper-energetic pair instability, supernova from stars over 130 solar masses produce detectable waves. Or maybe we're missing something fundamental about how gravitational waves propagate through the turbulent debris of an exploding star. Future detectors with sensitivity tuned to lower frequencies might finally hear these cosmic whimpers, revealing whether supernovae are simply shy, or if we've been missing a key piece of stellar physics all along. What's clear is that every undetected supernova isn't just a non-event, it's a clue. The universe isn't being quiet, it's telling us we haven't learned how to listen properly yet. Right now, gravitational wave astronomy is like listening to the universe through a keyhole. We catch glimpses of cosmic crashes, but the full symphony remains just out of reach. That's about to change. A new generation of ground-based detectors like the Einstein telescope and Cosmic Explorer are poised to rip that keyhole wide open, transforming our eavesdropping into a front-row seat to spacetime's greatest hits. These aren't just upgrades, they're quantum leaps in sensitivity, designed to catch whispers from collisions so distant or faint, today's observatories wouldn't blink. Take the Einstein telescope, slated for construction deep underground in Europe by the 2030s. This triangular behemoth will ditch LIGO L-shaped design for three 10-kilometer arms arranged in an equilateral triangle, boosting its ability to pinpoint sources in 3D space. But the real magic lies beneath the surface. Buried 300 meters underground to escape seismic noise, its cryogenically cooled mirrors and quantum-squeezed light will reduce interference to near zero, making it 10 times more sensitive than current detectors. The result, instead of catching a few dozen mergers a year, it could spot thousands, from the faintest neutron star tangos to black hole collisions halfway across the observable universe. Then there's Cosmic Explorer, America's answer to the next-generation arms race. Imagine LIGO 4-kilometer arms stretched to an astonishing 40 kilometers, a length so vast it could detect gravitational waves with frequencies too low for current instruments to register. This monster would peer deeper into cosmic history, potentially catching mergers from the universe's first billion years, when black holes were forming in environments we can barely simulate. Its design focuses on the mid-band, frequencies where countless neutron star binaries hum before their final plunge, offering a census of these systems that could reveal how often they collide and how much gold they're forging. What's truly revolutionary isn't just the volume of detections, but the detail. Current signals often arrive as fuzzy snapshots, like grainy photos of a speeding car. Future detectors will deliver 4K slow-motion footage. With Einstein telescope's precision, we could measure a black hole's spin to within 1%, or spot neutron star quakes' vibrations in their crusts before they merge. Cosmic Explorer might even catch the minute tidal distortions as a black hole slowly shreds a neutron star, revealing the star's internal structure like a cosmic MRI scan. But the real jackpot, these detectors won't work in isolation. Paired with space-based observatories like LISA and traditional telescopes, they'll create a multi-band gravitational wave network covering frequencies from the hours-long rumbles of supermassive black holes to the millisecond chirps of stellar collisions. It's the difference between listening to a single instrument and conducting an orchestra where each section reveals harmonies the others can't. The data deluge will rewrite textbooks. Imagine catching a neutron star merger every week, building statistics to finally understand how often they produce heavy elements, or discovering black holes in mass ranges we've never seen, hinting at exotic formation channels. There's even a chance we'll stumble upon something entirely unexpected, a signal that defies all models, forcing us to rethink gravity itself. One thing's certain: the golden age of gravitational wave astronomy isn't behind us, it's just tuning up. And when these detectors switch on, the universe won't just be whispering, it'll be shouting. Gravitational waves don't just help us decode the universe's past, they might hold the key to its ultimate fate. Every ripple in space-time carries clues about how the cosmos expanded, how it's structured, and where it's headed. And if we listen closely enough, these cosmic messengers could reveal whether the universe will end in fire, ice, or something far stranger. Take dark energy, the mysterious force accelerating the universe's expansion. For decades, its nature has been one of cosmology's biggest puzzles, but gravitational waves offer a unique way to measure its effects. Unlike light, which gets stretched and dimmed as space expands, gravitational waves pass through the cosmos unaffected by dust, gas, or intervening matter. This makes them pristine yardsticks for cosmic distances. By comparing the gravitational wave signals from merging neutron stars with their observed brightness in telescopes, scientists can calculate how much the universe has stretched since the waves were emitted, a direct probe of dark energy's influence over billions of years. Future observatories like LISA and the Einstein telescope could track these measurements across unprecedented distances, mapping the expansion rate with precision that might finally distinguish between competing theories. Is dark energy a constant force, as Einstein's cosmological constant suggests, or does it evolve over time, hinting at undiscovered physics? Gravitational waves could settle the debate once and for all. But the implications run even deeper. Some theories suggest dark energy isn't uniform. It could clump in certain regions of space, creating invisible topological defects that subtly warp passing gravitational waves. These distortions, if detected, would reveal structures in the cosmos we never knew existed. Even more radical is the idea that dark energy might interact with gravitational waves in unexpected ways, perhaps slowing them down or altering their polarization. Such a discovery would rewrite our understanding of gravity itself, exposing a hidden connection between the universe's expansion and the fabric of spacetime. Then there's the ultimate question: how does it all end? If dark energy keeps accelerating the universe's expansion unchecked, galaxies will eventually vanish over the cosmic horizon, leaving our descendants in an isolated, fading void. But gravitational waves might offer early hints of this lonely fate. As supermassive black holes merge in distant galaxies, their ripples could serve as mileposts for the expansion rate. If we detect fewer collisions than expected at extreme distances, it might mean the universe is stretching so rapidly that some waves never reach us, a quiet harbinger of the Big Rip scenario, where even atoms are torn apart. Alternatively, if gravitational waves reveal unexpected variations in dark energy's strength, it could support cyclical models where the universe eventually collapses in a big crunch, only to rebound anew. The most mind-bending possibility: gravitational waves might carry echoes from the universe's birth that predict its death. Inflation, the explosive expansion moments after the Big Bang, likely generated primordial gravitational waves still resonating today. Their frequency and amplitude could reveal whether the vacuum energy driving inflation persists in some form, perhaps as dark energy's precursor. If so, the same force that birthed the cosmos could ultimately tear it apart. What's astonishing is that these ripples, born from black hole collisions and neutron star crashes, could illuminate truths about existence itself. They're not just cosmic footnotes, they're the universe's way of whispering its deepest secrets, from the first flicker of time to the last gasp of entropy. And as detectors grow more sensitive, we're not just observers of this grand narrative, we're learning to read the final chapters before they're written. From the first faint whisper of colliding black holes to the eerie hum of primordial spacetime, gravitational waves have shattered our cosmic perspective in just a few short years. We've witnessed black holes merging in ways Einstein never imagined, some spinning backward, others weighing more than theory allowed, and even a few that might predate the stars themselves. Neutron star collisions became our alchemists, forging gold in cosmic kilns while gamma rays lit up the sky like celestial fireworks. We've caught spacetime ringing like a bell, tested relativity in gravity's most extreme regimes, and even glimpsed hints of wormholes and cosmic strings hiding in the data's noise. This isn't just a new chapter in astronomy, it's a whole new language. For centuries, we studied the universe through light alone, like watching a silent film. Now, gravitational waves have given the cosmos a voice, revealing everything from hyperfast black hole spins to the violent births of heavy elements. They've exposed flaws in our stellar models, unveiled unseen populations of black holes, and even hinted at dark matter's secrets. Every detection is a Rosetta Stone, translating the universe's hidden dramas into something we can finally understand. But here's the most thrilling part: we're just learning to listen. Future observatories like LISA and the Einstein telescope will catch frequencies we've never heard, from the stately dances of supermassive black holes to the faint echoes of the Big Bang itself. We might soon decode quantum gravity in the ripples of a neutron star or spot a primordial black hole drifting through our solar system. The universe is teeming with stories we've yet to hear, written not in light or dust, but in the very fabric of space-time. So stay curious. The golden age of gravitational wave astronomy isn't on the horizon. It's already here, unfolding with every passing second. Who knows what we'll discover next? Maybe you'll be the one spotting an anomaly in the data or pondering a cosmic mystery that rewrites the rules. The universe is speaking. All we have to do is keep listening. If these discoveries left you as awestruck as they did us, let us know in the comments which revelation blew your mind the most. And don't forget to subscribe so you won't miss the next breakthrough. The cosmos has plenty more secrets to share, and we're just getting started.